is by Sanjit. He's going to tell us about decihertz gravitational wave astronomy, and I'm already super intrigued by the cartoon on your first slide.
This is stolen from somebody, but I could not find from where I stole it. So I could not acknowledge the person. Okay, so I will try to make it as interesting as possible. Like, still after all it is gravity wave observations. How interesting can you make it? But it's of course very interesting. So what I'm going to do, because it's a neutron star meeting, I'm going to mix some of the neutron stars part, and then I also promise some of the cosmology part, and then it will be a little bit of hodgepodge, but I will try my best to make it as smooth as possible. And as you can see, so this, I'm going to advertise something about this decihertz observatory, where I personally feel that, and many others feel that India can get into. Of course, and many others can get into, and this is the place where there is a vacuum right now. And so basically in between I link to that, and then in the end we'll come to the timeline and context right now. So I think these things have been discussed in great depth in this meeting. Unfortunately, I could not attend the meeting, but we know that it was a great meeting, and I wish I could. So right now, here is the situation, and this is pretty exciting. The thing is that if you imagine in 2015, when advanced LIGO was about to start taking observations, the primary questions in people's mind was that whether advanced LIGO is going to see anything, and what if it does not see anything. And today, in about 5 years, in a very short time, that whole question has disappeared, and we are very much wondering we have about 100 detections, like plus minus 10 and so on, depending on which algorithm, etc. you are using. And we are thinking what astrophysics we can do, and how to increase this number, how to do cosmology, and all kinds of things. So even though people are skeptical about new fields of astronomy and new windows in gravitational waves now when we talk, initially when we used to talk about gravitational waves, we used to call it a new window of astronomy, missing the fact it is actually a set of windows in astronomy, meaning like in electromagnetic astronomy there is X-ray, there is infrared, etc., etc. So here also there are different windows, and with only one window we have achieved quite a bit in the last 5 years. And so in connection to the neutron star meeting, what did we learn from the most interesting, in my opinion, the most interesting detection that we had, that is GW170817. I'm not getting into there are many other discoveries, of course, different black holes, intermediate mass black holes, etc. But I'm just focusing on the one which would be probably most relevant, and then so that we can come to the point very quickly. And what we learned is that this picture people had, that binary, that neutron stars go around, then they merge, and then probably I have this animation also. They merge, and then they create this kilonova, and which basically can explain a significant part of the origin of the heavy metals, etc. So these things were all theorized, but this is through this observation we had a very good idea about how the physics in neutron stars work, and the hope was that many such observations will happen, and we will have many electromagnetic follow-ups, and then we will get much more information about these sources, because this happened in 2017. Unfortunately, that did not happen. We were very lucky that right after, in the 3rd year of gravitational wave astronomy, we detected a source which was at 40 megaparsec, and we could do a full electromagnetic follow-up in multiple wavelengths. We were basically, we are just statistically favored. That's what I would say. Then how do we move forward? So I'll come to that in a moment. We also had a pretty good idea about stiffness of the neutron stars, we know that softer neutron star equation of states were preferred over the stiffer ones. And then again, this did impose some of the conditions on the equation of state and so on, constrain some of it, but hardly, I mean, there is a lot of room to do. Now, in all these measurements and physics that we want to do, the important thing here is that there are two important things. First, we need to measure the component masses very accurately, okay? That is one, so that all the degeneracies in these other parameters can be broken as much as possible. The second part is that if we can have an electromagnetic follow-up of these events involving neutron stars. These two, please remember these two. We are going to come to this later on. Okay? All right. Now the other part of constraining Hubble constant with GW 170817, as you know, there are, I don't know if anyone gave a talk on this here. So there are different precise measurements. I mean, two highly precise but competing measurements of Hubble constant. The green one is the measurement from cosmic microwave background observations. This orangish one is from supernovae. They are all they have few percent accuracy, but they don't match. They are not compatible. So at least one of them is wrong. It could be both of them. So we need complementary measurement to see which one is correct. Then I don't think this is what you can see it, right? Otherwise you can, yeah. So this is the measurement which came from this binary merger, binary neutron star merger. The error is pretty large. The hope was that several such measurements will be done, and then we would be able to distinguish this. So this is this. Now I think it has almost, no, it is still there. I cannot see it properly. This is this Nature Later paper which was wrote by Daniel Holge and so on and company, where they showed that we could have by 2026 or so, we could have 1% or 2% measurement, I think 2 or 1%, 1 or 2% measurement of Hubble constant, which would be able to break this degeneracy. And you can see that he thought we will have, so this is, oh, by the way, are there people on Zoom? Then I should use this cursor.
Yes, people are
on Zoom, okay, fine. Sorry, then I'll use this one. So the hope was that, see, this is O3, and already there were like few, not 10, but like a few neutron star mergers which will be observed in 2019 and so on, and then if people understand what I'm saying, so which may be okay. Okay, so basically in 2022, so this is 2023, by now we will have about, so more than like about 20, I think, binary neutron star follow-ups, which did not happen. Okay, we are far from it, and now we know that these rates are probably an overestimate. Then, okay, so just to complete this story, so this is the cosmologists are very excited also about these measurements. These are the measurements of Hubble constant for different years, which was published by Planck. These are astronomical. This is like for early measurements, and these red ones are similar, and this magenta one was from gravitational wave, and the hope was that it will slowly reduce. But that did not happen. Now the question is that, so okay, this is where the situation is, so how do we actually get this measurement better and faster? So that's the question. So how it was done? So this, after the event was detected by Orlando, we had it in a decade, but then it was sensitive enough, which was enough to localize the source. All these electromagnetic observatories made followed up the source for immediately following the event for like days and weeks and so on. Okay, and that we all know. I think Varun Valera must have covered this in his talk. So I will not get into this. Several Indian observatories took part in that, and because it has to be a global effort and so on. So I'll just skip some of these. Okay, maybe I can show this one. Okay, maybe I can skip this one also because Varun must have covered this. So basically, the idea is that if you have multiple detectors, then you can do the localization very well. So, so these are like error circles on the sky from when 2 detectors could detect, and these ones are when 3 detectors were sensitive. Not necessarily they're detecting. Sensitivity is good enough. And this is like another cartoon, like if LIGO India was operational, when the first detection happened, this error bar could be much smaller. Okay. So the key here is localization. That it is very important to have very fast localization of the events. I mean, it is like just a cartoon, like how GPS satellites work. Like you need 3 detectors for proper localization. But then, because the detectors are not sensitive in every direction, you could cut out some of the rings on the sky. Okay, so I will come back to this, that why it is relevant and so on very soon, that how we can improve the situation with a decihertz detector. That is the whole idea. So just before that, so what are the targets right now? So there are many very interesting unanswered questions. I can read some of these. For example, where, when, and how do these black holes and their binaries form? We still don't know this. Even with 100 observations, we have some ideas, but actually we don't know whether they are forming in globular clusters or in relatively empty spaces in the galaxy, or there is a mix of this. This has to be answered. Probably required the exact measurement of the spins and so on. So this is another thing that we need. So again, how do we break this degeneracy? For this also, we need the observations of the early in-spiral part very precisely. Then how many such binaries these things are there, what is the distribution of their masses and spin and so on. Like, do intermediate mass black holes exist? Well, partly answered. We have probably something like at 150 solar mass and so on. But are there intermediate mass black holes of 1,000 solar mass and so on? We don't know yet. These things are very important for cosmology, right? I mean, if some seed black holes merged and formed they hierarchically grew, then the signature would be different from if something big was there. So there was a big seed black hole in the very early universe from which the structures formed. Is general theory of relativity is the ultimate theory of gravitation? Again, like this is again another question. How do we address this? I mean, I don't have another slide, so let me tell you how we do this part. What people do is that they get the masses of the component masses from the in-spiral part. Then they look at the in-spiral part will tell you the component masses and the orbital angular momentum, which you should match what you observe in the ring down, final ring down part, and then there you observe the spin and the total mass, and then you compare and see that whether they match or not. This is one of the primary tests of general relativity. Then you could also do other tests like ring down phase of a bigger black hole which has higher signal to noise ratio. Again, all this part would be much better if we had a very precise estimate of the mass and spin from the early in-spiral part. Okay. Now, okay, again, what is the value of the Hubble constant and so on. So there are many questions. I think you know all this. And then there is one more thing. And the thing is that these are the maps of the universe in different electromagnetic windows, starting from radio to gamma ray. I hope at some point we will have similar maps of the universe in gravitational waves. Right now, what we have are these transients. This is not even a static map. These are like some spots on the sky. And hopefully, we'll get a map like this soon. I have a feeling that the first map of the persistent gravitational wave sky may actually come from in nanohertz, because you are going to probably it may happen that in nanohertz frequencies, the stochastic background will be observed first, and the stochastic background is a persistent background.
Why do you say that?
Meaning a stochastic background is, it is like the cost.
Pick up at the nanohertz. Why do you think it will be picked up at nanohertz? It completely depends on the mechanism that generates the gravity.
This is not the primordial one. I'm saying the astrophysical one. But the astrophysical one, which is produced from supermassive black holes, etc. I mean, see, it is. We don't know which source is emitting when, but it is persistent, right? I mean, the spectral features, etc., are not changing. So this is another interesting goal that we have. Okay. So now we go to the next step. So what should be our next steps? Like, of course, we have to build. I had a lot of stuff, but I don't have to read through all this. Essentially, the idea is that we need to build detectors at different bands. The present detector sensitivity should be improved. So there are these present LIGO detectors. We hope that their sensitivity is going to be improved. I'll come to that to certain levels. We should have next generation detectors. We should go to different bands and so on. In the Indian context, the next major steps would be LIGO India, which we hope will come up in the next few years, and then hopefully we should take part in some of the space-based detector one. I did not mention the IPTA part, but that is kind of implied because it is already there. This is to motivate something else, which you will see. Okay, so here this is going to be the map in the of the network, sort of. This also you know. So here is the thing which is happening. So now I gave you essentially what has happened sort of so far, and we are going to see what people are doing right now, not just thinking, and then we will see where how a decihertz detector can where it can come in. So this is the future for the ground-based detectors. Okay, so this I think many of you have seen this. I will just come to this. So this is advanced LIGO's O3 sensitivity. This blue curve is LIGO A+, where LIGO India also should come in. Now if you look at this very nice plot, we are here, okay? This yellow side are binary neutron star mergers, and this side, right one, white dots, are binary black hole mergers, okay? This sort of light blue dashed lines is O3 sensitivity. And here also you see that a corresponding line is there. You see in the black hole mergers, we have sort of started getting into the crowded region. For binary neutron star, we are basically in an empty part of space, and no wonder that we did not detect anything so far. Of course, those rates have gone into this. Now, what is going to happen with A+, that is when LIGO India comes in, is that we would be able to go here in this part. Okay, that is quite a bit in the crowded part of the universe where lot of binary black hole mergers are happening.
You mean when LIGO India is added, or only with LIGO India?
No. When it is added to the, so we, assuming that by 2028, LIGO India comes with A+ sensitivity and so on, this will happen even without LIGO India. Okay, but then it will be slightly lower, maybe somewhere here, some little bit. It's not just that the number matters. Also with LIGO India, the localization will be improved. I will come to that. Yeah. So, but on the other hand, if you see this side, you see that even with A+, we are basically in the empty part of the universe. Okay, we would not be able to see many binary neutron star mergers. So then what is going to happen to our neutron star equation of state, Hubble constant measurements, and all those things? So this is the problem. Now, what is the plan for the present LIGO detectors? We are hoping that they will be upgraded to a next generation sensitivity called Voyager. Okay, the sensitivity will be improved by, let's say, factor of 2 to 3 from A+. Voyager kind of takes us to the edge, but still not too much, okay? But on the other hand, at least you will be able to see quite a few of these binaries. Okay, we'll see more quantitative things later on. And then what is the plan for the next generation ground-based detectors? So there is this Cosmic Explorer and Einstein telescope, which are going to be 10-kilometer class detectors. Okay, so this is Cosmic Explorer present hope wish, that is 40 kilometer, and this is for Einstein telescope, which is like 10 kilometers. Okay, triangular, and this is a design for Einstein telescope. I mean, these things can change, but this is where it is. Now, important thing to note is that for both of these detectors, the site surveys, etc., have been significantly completed. So the chances that India can get into one of these detectors, that is host one of these in India, are quite slim. That is, yeah, meaning we can contribute to these detectors by providing technology, making components, etc. But hosting one here, the chances would be pretty slim. This part, what I'm saying, that we will contribute to this, will anyway happen. That is, there is no doubt about that. Okay, now, and let's see what is the situation with in the space-based. So there is, in 2035, the laser interferometer space antenna, which is called LISA, is scheduled to fly. This, whether it will have 3 arms or 2 arms and all those things are getting finalized, but this is going to follow the Earth, and it is going to observe in the millihertz band. There is a Chinese mission called Tianqin, which is also going around at the same time. These two observe in the millihertz band. Here there is a detector which was proposed called decihertz interferometer gravitational wave observatory from Japan. This is, the plan was that there will be constellations of 3 spacecrafts which will have Fabry-Perot cavities. Okay, I will not get into that what exactly it means, but it will be like ground-based detectors. They will fly, and there will be eventually 4 of them. 4 clusters, and you can cross-correlate the data between those. It will be like kind of like radiometer, and they will also follow the Earth. They will be in the heliocentric orbit and then follow the Earth. However, this mission is not yet funded. Okay, this is the present situation in the space-based detector. There is also one more detector called Taiji from China, which has been proposed. So what is the situation with LISA? So LISA's Pathfinder mission was launched in, I think, 2015 or something, I forgot. Now, this was the noise requirement for LISA Pathfinder. If this could be met, then people would be convinced that, okay, this mission is worth pursuing and it can be made. And this other line is LISA's requirement. What happened is that LISA Pathfinder did better than LISA's requirement. So this is really, really convincing, and this mission is flying. This also shows that a space-based, I mean, it is not really a science fiction. It is very much possible, and then people can aim for that. Yeah. That is right. There are many other. There are other things. I mean, yeah. I mean, you know, but this requirement, I understand, is also for that, right? It is not taking everything in.
From Americans, and that didn't happen. So.
Yeah. But these requirements were placed based on only the acceleration noise measurement, right? I mean, so that way it was met. Yeah.
Maybe follow secrecy, or maybe
No. So this is just one part of it, that you can use the micro thrusters. No, you cannot do astrophysics right away, because that requires much more money.
So then, in what sense it was better? I mean, so
this is the acceleration noise, that you can have a drag-free environment in the spacecraft. The idea is that the test mass has to be in free fall, that is following a Keplerian orbit, and the spacecraft has to not to touch the test mass, but then keep a distance from it and then follow. So in my understanding, that's what was proven here.
Essentially, micro clusters.
So, yeah, that you can maintain the distance from the test mass. Okay, and that is supposed to be the primary challenge. The other parts, that interferometry, etc., is are also challenging, but we hope that there are lesser challenge. I mean, this is a bigger thing. Okay, so now what is going to happen anyway? I mean, people are kind of convinced with LISA and it is funded and it is going on. Now, what is happening? Then what LISA is going to do? This is also quite a popular plot. You see that here there are these binaries, okay, which are in the inspiraling phase. LISA is going to see them. And then these binaries are eventually come to the LIGO band or ground-based detectors band, and then they are going to merge, okay? Now look at this timeline. This is 10 years, okay? And this is 1 hour, okay? That means if you could, if LISA saw these sources, you would know few years in advance that they are going to merge. But now let's calculate a little bit. That LISA is flying in 2035. Let's say it observes for 3 years. It's a 2038, and then it knows that in 5 to 10 years something is going to merge. So that is like we are almost approaching 2045 to 2050. The problem is that many of us may not even survive that long. So we need to do something little quicker than that. And you see this band here. Here it is 1 hour. If we have a detector here, okay, quite soon, then we would be able to, that is, let's say 2035 or so, we would be able to predict few hours to few minutes in advance that there is a merger is going to happen. And then this also gives you the opportunity that this part, the binaries spend a large amount of time here than here. So the masses and spins are going to be very accurately measured from the in-spiral part itself. So you are almost ready to focus on exactly what you want to do, that is test of gravity, let's say you want to do electromagnetic follow-up and so on. Now why it is very important for electromagnetic follow-up is because these are transient sources. So if you know where exactly the source is going to happen, which will also can be obtained from the modulation of these detectors, then all the big telescopes could tile the sky optimally, as long as they are not doing politics and everyone wants to only focus on the maximum of the the posterior, which is very unfortunate, which is what is I understand is happening now. But if we can wisely tile that space with all the big telescopes at that time, we are talking about 2035, even TMT may be online at that time, let's hope so, and then you can do very deep follow-up. That is, the source does not have to be at like 40 megaparsec or 100 megaparsec and so on. We should be able to go beyond. That has an immense effect. I will come to that I will show you that what happens. So now I will present some of the results which were done for a detector which was proposed by the Caltech group. Caltech and Chinese group, they made this proposal called Tiango. Now here, so you see that this blue and the red are the Tiango. So this one and this one. This green one is Decigo, which I showed before. The thing is that Decigo is a bit too complicated. It had these triangular shaped designs with 3 arms with Fabry-Perot cavities. It gets technically quite challenging. On the other hand, if you could just take an interferometer which is operating right now with like an L-shaped detector and just fly it, we know how to operate that. So that will be much easier. But the sensitivity will be less. But it's not too bad. See, this is Decigo, and you have a gap here. You could still do a lot of science there, and that is, so next few slides will be on that. Okay, so and this is the track of the binary. You see that the binary spends quite a bit of time at very high signal to noise ratio here, and then merges in the ground-based detectors band. So what you can do? So first of all, early warning. See, these are, suppose you take nearby sources, 50 to 50 megaparsec or 200 megaparsec. These are two curves here. You see that with the, let's only talk about the 200 one. 50 of course will be even better source. And this is the time to coalescence in days. So this is 1 day, okay? The shades represent best 50% and 90%. So you see here, this 1 day and 90%, that is 90% of the binary neutron star mergers will have better than 0.01 square degree sky localization with this detector. How this is possible? How did it happen? Now, the thing is that this, so first of all, this will happen anyway. I'll come to this other part. This will happen directly from the time of flight. I mean, during just by this thing itself, Tiango itself, that decihertz detector, because it will, there will be modulations, etc., from which you can get this. But then, even better things can happen. So this already will be enough up to 200 megaparsec to tell all these electromagnetic observatories that just point there, something is going to happen there. And this is extremely small, so they can go really deep and get, I think, you never know, even a neutron star, black hole neutron star follow-up may be possible with this. Okay, so now let's go a little further. Now, if we are looking at much farther, so this is like gigaparsec, okay? Now with gigaparsec, with the space-based only, you don't do too good, okay? This orange one is space-based only. With ground only, also, it's slightly better, but not too much, okay? Because, you're looking, the space-based one is only using an antenna pattern modulation, and the ground one is using a baseline which is like 1,000 kilometers. But when you combine ground and space, you get again extremely, like at 10 gigaparsec, you get 0.1 square degree resolution. So how is that possible? This is happening because the space-based detector could be 1 million kilometers away from the Earth. And now you see one thing which I showed before. Here, you see that decihertz detector has a very big advantage as compared to the millihertz detector. A decihertz detector has a significant overlap here with the ground-based detectors. So this part of the decihertz detector was good enough for prediction, forecast. But this part, it can do simultaneous observation with the ground-based detectors with an effectively 1 million kilometer baseline, but at a much cheaper price than LISA. So that gave us this enormous sensitivity, okay? And then what do you do? What kind of physics you do with that? So here is the amazing thing. So you see that this blue patch is Hubble constant and omega matter measurement with 3, let's say, Hanford, Livingston, India, LIGO India, Voyager configuration. And then if you have, if you add this Tiango, which is the red one, you come here. This is enough to break the degeneracy of Hubble constant measurement. You can go even better and so on, like if you put DCGO and 2 Cosmic Explorer and 1 this thing and so on. I mean, you can do all kinds of like science fiction level things, and this can become so small. It's an extremely precise measurement. But it goes beyond that. With the Tiango and these 3 detectors on the ground, I'm saying Tiango, but it can be any decihertz detector. You see this red error bar here. There is an error bar here, see, red colored in the inset. You see that this is very small, and it is going up to redshift of 0.3 or so. Let's say 0.2. You can measure not only the Hubble constant, but the Hubble parameter variation. This can tell us, this can constrain significantly the dark energy evolution and so on. Okay, I will speed up. So there are different things which we can do, and there is this paper is actually pretty good. And sorry, this is not the right one. Actually, this reference, this is the right reference. This is from that one. So you can. So there are different things which one can do with a decihertz detector. Now I will shift a little bit to the neutron star part again, because this was more towards cosmology. And okay, so I'll go quickly. So these are the present upper limits.
All these are, you're talking about individual sources, not the stochastic.
Not yet the stochastic. Yeah, I am coming to the stochastic now. So yeah, so these were, but then we're using mostly neutron stars. So I thought that this audience would be, yeah. So these are the present upper limits on the neutron star, spinning neutron star from LIGO. But I will move that, and I will connect that why this is also important for cosmology and the stochastic background measurements. I will come to that this is also crucial. But let me just skip these parts. Okay, I will come to this part. Okay, this is what we are doing right now. You see that this is the population of spinning neutron stars in our galaxy. This is the predicted population from the ATNF catalog. And these are the millisecond pulsars where presently the limits are being put from LIGO and so on. Now there is this huge population. Actually, this is supposed to be some 10 to the 8, 9 pulsars in our galaxy, which are at much lower frequency, and we are presently not paying attention to it, right? Now these ones are falling in the LIGO band. That's why we are paying attention. Now, but the thing is that this large population is maybe emitting gravitational wave at a lower amplitude, because the amplitude goes as f squared, the frequency square. So if the amplitude is lower, then the frequency is lower, you have lower amplitude. But then the number is very large. So this can create a stochastic background in the decihertz band. Okay? So I will not get into too much of details about the stochastic background, other than saying that, okay, I'll very quickly go through these parts, that how stochastic background is detected, and then go back to the other part. So basically, if you have data from two detectors which has some uncorrelated noise, that is the noise correlation between noise in the two detectors have no correlation, but the signal can be correlated, then you can do this kind of cross correlation search where you cross correlate with some optimal filter. Essentially what you end up doing is Earth rotation synthesis imaging, which has been covered here for many pulsar timing. People will obviously know this. So you basically account for the delay in receiving the signal, and then keep integrating, and then you can make a map. And then this was also done for, okay, I will actually skip quite a bit of these things because I want to keep some time for the discussions. All I wanted to say here is that suppose you have hot spots on the sky, let's say cluster of galaxies which has a large number of millisecond pulsars, one could also try to detect the stochastic background from that region using this kind of radiometer technique. Here the estimation was too high, because they assumed like 10 to the minus 5 electricity and so on. But this is in principle possible, and we showed essentially that if you have a stochastic background created by the high redshift sources, like let's say millisecond pulsars but spread up to redshift of 3, then the background gets dominated by the isotropic part. But then if the background is dominated up to, let's say, of redshift of 1, then they will show up as bright spots on the sky. And the contrast is pretty high, meaning you can have like one contrast of 1000. That is, if you point to the, meaning this is pointing in its software, if you make a map of the sky, the parts where there is no cluster versus part where there is a cluster, you have signal to noise ratio difference would be about 1000 and so on. So this is possible. This is like, Olber's paradox sort of thing, that will you be able to see any anisotropies and so on. As I said, I'll come to this, that why these things are important. So this kind of upper limit maps are being produced by LIGO at different, broadband upper limit maps and so on. But this is not of it's not the most interesting thing. I'll tell you later. Alpha is the spectral index. It is like 0 is an inflationary background. 2/3 is the background created by compact binary coalescences, and 3 is essentially from pulsars. I'll actually show you later on that why these things are coming, because I'm just trying to connect from here and there. So there were some algorithms which we developed which actually made these things possible. But now again, connecting to the pulsar part, this is the latest thing which we did, latest meaning this is a LIGO-Virgo collaboration paper. This was based on these data folding techniques which we used and so on, which may also be relevant for pulsar timing. So this, what you see here, is that earlier what we used to do, we used to make a broad maps of the sky for different spectral indices, like this 0, 2/3 and so on. We did not have the ability to make a map at every frequency. This is basically a this is pixel index, and this is frequency. Each row represents a map of the sky. So here you see this is a map at some frequency, this is at 200 hertz and so on. These are some example maps which are shown. So each one of them is a map. Or you could look at one single pixel, one direction, and this one is basically telling you the upper limit at different frequencies. Okay. So this how would it matter for the pulsar searches? So right now, because of computational reasons, we cannot do a full sky continuous wave search. That is, at every direction we cannot look for narrow band continuous sources. But what is possible is that suppose you have some injection. I mean, this is shown with simulations. Suppose you had some of those injected pulsars. Then your distribution, the observed distribution, which is actually shown by the zero lag, that's how we do it. That zero lag means the direct correlation, and if you add unphysical delays, then it gives you the noise background. This will have some tails like this. And you would be able to identify those outliers which may potentially host a source. Then you pass on these specific points to the groups who are doing matched filtering based searches, and they can do a follow-up at those points. So this is the present thing, and there are many details which are people are working out different things there. But why all those things are important? Now I am coming to the point Sriram was trying to say. See, this is kind of like the understanding of the history of the universe and so on. From this point, the CMB onwards, I think we have a slightly better understanding than what happened before CMB. We can do with, we know that inflation is necessary and so on, but there is no direct observational evidence. Other than that, what we are doing is reverse engineering. We are saying that if this does not happen, like if there is no inflation, you cannot solve the horizon problem and things like that. So we need some direct observational evidence from this side. That is, everyone wants to detect the primordial gravitational wave background, to be specific. And then there is the other gap also in cosmology, like the dark energy part. And I already told you that how the decihertz measurements of the variation of Hubble constant, Hubble parameter, can give us some handle there. I will skip all these. Sriram covered all these in great details. So what I am going to focus on is on this one. So there is a hope that, see, this is the stochastic background, and this is frequency. Okay, this dashed line shows the stochastic background from inflation. These are the backgrounds which are created by sort of astrophysical foregrounds. There is a hope that there is in this band in decihertz, there is a window where there is minimal astrophysical background, foreground. So this window is very interesting.
What do you say that? You just said that there will be the inspired place that we can.
Right. I'll come to that. So this is from one of these papers which says like this. But the thing is that even if there is inspiring, those lines are there, those can be subtracted out. Once you have the detection, you know that this line was present for the last few years, so you can or few hours, so this can be subtracted out. But even then, there is exactly, so the foreground cleaning. So there is a chance that we will be able to detect the probe or constrain the primordial background here, and this was one of the primary motivation for DESIGO. But life is not going to be that simple, and this is the evidence that this was the bicep detection, right? They thought that they have detected the primordial gravitational wave background, but it turned out that this is just the galactic dust what they have detected. So this is what we have to be careful about. This is this Ariana Renzini and people and company produced this nice landscape. You see that different detectors are plotted like this, and different foregrounds which are expected, the primary ones are plotted this one. The point is not to focus on individual this thing. The point is that what we have to do is a multi-band analysis for foreground cleaning. If we know how many, so this is the tail which was not present in the other plot. You see that it is not like there is nothing there. This is decihertz here. So this is the produced by the binaries, but then there is a tail here. So that, but on the other hand, if we know this very well, this part, we know how it falls. I'm almost done. This, I'll take 5 minutes. Yeah.
Very short question. The cyan line for the inflation, what exponential ratio it assumes in that?
I think 0.01. This is 10 to the minus 16. Yeah.
0.01, then if it is not there at 0.01, then it is going to be even down.
Yeah.
Unless there is some exotic or some inflation
Yeah. Then it could go up there. Yeah. I mean, there is a chance that during reheating this can also go up and things like that. So, but the thing is that the point is not exactly like where it is. The thing is that there will be this part. If we know this part very well, then we would be able to subtract off this part. This is also true for the pulsars I talked about, right? The big pulsar peak that we are ignoring right now actually may have contributions here. So in the end, this may happen in it may take 50 years to detect this background, but I'm hopeful that it will be detected at some point. I mean, I'm alive or not is a secondary question, but we have to keep doing, take the steps so that we can reach there, right? I mean, that is the whole idea. What? Leela? Oh, okay. You mean that? So this is PPTI, yeah. So, but the lunar part. So lunar part is also, so they are also in lunar interferometer is also in the decihertz band. Right, so that is, these things are all in the same part. The problem is that the lunar part, we have to see carefully, and there should be more detectors. See, the moon also has seismic activities. So we have to be careful about that also, right? I mean, that how much...
The argument is it's better than, but anyway, we can...
It can be possible. It is all possible, yeah. But the point is here is that we need a decihertz detector. That's the point, or more. Not just one, because then we can do correlations.
One very small thing that what I'm saying is that you are saying that okay, maybe 20 years or 30 years or even 50 years. Let us. Okay, no, but what I'm saying is that light bird is going. That has a threshold of 10 power minus 3, and CMBS4 that will be 10 power minus.
Correct.
5 into 10. So we may not have to wait for that long. So that might be, for me, it is very interesting in terms of if there is some physics beyond the standard slow roll.
Well, perfect.
That will be very good.
Yeah, that will be. So you would not be able to, without multiband, without looking at this part. See, if you see only this part and not this part, I don't think you would be able to constrain all the.
Not at small scales.
Yeah.
No, they're talking about small scales, right? These are very...
No, here small scale. The light bird will be here.
Yeah, no, what I thought that you were saying that if we see the stochastic background at that level, then we can back calculate that the tensor to scalar ratio was 10 power minus 2 during inflation. Yeah, so that is what I'm saying, that it is very difficult to, so Lightbird might already see it in 10 years time rather than we have to wait for that.
Correct. So there are two things here. One is that I think you just this would not tell you the constraint the inspirational model, and the second part is that this will be I will call it like the Hull-Stellar detection. It will be an indirect detection, that is imprint of the primordial background on CMB, but a direct detection is always going to be fun, right? I mean, you see both of them would be there. I think somebody, yeah, you had, okay. Since there are questions, I'll take little longer. Yeah.
What about BBO?
BBO was also like the DeciGo, but it is no longer funded, meaning, so nothing is funded, but it is no longer pursued, meaning the hope for funding has gone away from there. So, yeah. Since there are questions, I'll take 2-3 more minutes to wrap up. I'm almost there. So, So these are this is for the decigo. Okay, let's okay, fine. Here I should show one thing. I mean, there are different configurations possible. You don't have to really look into the configuration, but typically, what people are thinking are 100 to 1000 kilometer arm length detectors with few watts of laser power in space. It could be in geocentric or in heliocentric orbit. Heliocentric would be probably better because then you get this bigger baseline and so on. So what you need to see here, okay, this part. This is, again, that omega GW is 10 to the minus 16. If you have these multiple constellations, which is why even another detector, let's say on the moon, would be nice, because then you can cross-correlate. Then you can maybe able to see this in few years. Okay, so this is the hope. But this means that you are only touching the background, so you are detecting it, but to claim that you have detected a primordial background, we need to say that all the foregrounds is understood correctly, which is going to be a serious challenge. It is, in my opinion, with both the experience of CMB and this thing, I think that is going to be the...
Those signals dominate.
Yeah, okay, not it's almost, I mean, very difficult to say.
No, but you had a slide that showed that possibilities in the previous slide.
Meaning this.
Next one. This one. Right. And scenarios where the primordial.
This one. No. This
is cosmic strings, right?
This is cosmic slings. Yeah, I mean.
Okay, I'm just saying.
I will be very skeptical about cosmic slings, though. I mean, I am more hopeful about this one.
Or FOPP.
Those are there, but I don't know whether that actually, meaning there is phase transition happened, but whether that solves our insulation problem is another thing. Yeah. Okay. So how does one go about it? Okay, so what I was saying is that, yeah, with correlation we may be able to see something, but we cannot go there immediately. It will be like what happened for LIGO, initial LIGO, advanced LIGO, and so on. So initially one can probably send a pathfinder and so on. This was planned for the Japanese mission, and then similar things we can do. So this is where almost I end. So the thing is that, so right now for in the Indian context, LIGO India is hopefully going to start soon, and then it is going to be done in the next few years, and we must plan the next steps. That's the most natural thing to do. For the third generation ground-based detectors, 10 to 40 kilometers, probably it will be difficult to find a site and so on, which can take years could be more than a decade and so on. Maybe a bit too late, but we can contribute in the instrumentation and so on. That way we can participate sort of actively. LISA, again, there is a lot of development has happened, and we have not started yet in terms of instrumentation. Again, we can contribute, but then it's not like, when you do LIGO India sort of thing, you also want to be in take a leadership role and do something new, which does not have to conflict with others. I mean, it is all two detectors, like when the Tianjin detector was proposed in China. People said that Tianjin and LISA together would be wonderful, because then you can have much better source localization, you can do stochastic background and things like that. So this is going to be very interesting. And so for that purpose, the best bet would be decihertz. Now there could be multiple decihertz detectors and so on. Yeah, I would not read the whole thing, I will stop here. Yeah, thank you.
Great, thank you. That was a really fun talk. Yeah, so we have 5 minutes more if we want to go past 5 for questions. Students first. Let's start with Avinash.
Okay, I have several questions, but both LISA and decihertz both are in the space, right? So why can't LISA observe in decihertz? What is limiting that fact?
So it comes out. Okay, let me. It's difficult to. No. It is the design is not possible. You cannot design a detector which is sensitive at every frequency band. This is almost an impossibility.
The distance between the
distance gives you the primary length. You can increase then if you try to increase it too hard. I mean, it is possible, but then you need to put much more money for the laser power, etc. So it is very difficult. Like for example, if you see here, this blue one has much longer larger bandwidth, but sensitivity is very low. So, but if you want to increase the sensitivity of the blue one, you have to go far below here, put a huge amount of money and things like that. I mean, this will be impractical in terms of money.
Okay. Second question. You have said that the young pulsars can exhibit the stochastic background, right? So how does
It's not young. I said meaning probably the old one, right? Meaning the low frequency one.
Low frequency are the young pulsars?
Well,
yeah, low frequency.
Okay, fine. If not the accreting. Yeah, not the ones not in binary. Yeah. So
means what do you say? In the millisecond pulsars, it's binary that will emit, but I didn't understand how exactly. Is it due to deformation in the shape or how?
No. What I mean, see, there are these pulsars there, right? This is this huge peak.
Yeah.
These are at like few hertz frequency. So if there are deformities there, they are just going to emit gravitational waves. We are not paying attention to them because they are not in our frequency band. No detector actually observes here right now. So, but then they are there. So you have to see this number here is very large. This is going to compete with the very small number that will be coming from here.
Okay.
Because the frequency is 2 orders of magnitude low, 2 to 3. So f square is going to be 4 orders of magnitude, 4 to 5 orders of magnitude low. But this number may be 4 to 5 orders of magnitude high. So, and then, but we don't know about the ellipticity part. Maybe here the ellipticity can be more, because otherwise here the spin down was faster. So maybe we have to see how exactly it goes, but we have to properly, I mean, right now what we are doing is that we want to estimate this and see where it comes.
Okay.
Any other students with questions?
So I remember some detailed discussion with Kurt, and his argument was that you have to remove every neutron star binary in up to, I think, redshift of 10 or something. He was giving me an estimate, I can't remember. I checked that from his arguments, and that's going to be very difficult simply because what you didn't mention, and none of these people worry about that, is that during that kind of spiral, you are essentially dominated by the chirp mass. Hence, the signal is a problem. Just like you have, 17087, you have big problem with the mass ratio. So the signal subtraction of the foreground subtraction is next to impossible, jeopardizing most of this. And this is a fairly valid point, and it has been ignored. But of course, right now the funding is more important, so you don't care about science.
No, it is not like that.
No, so that's a major,
So I will just go back a little bit here. So the hope is that with the third generation detector, see, we are talking about now far into the future. The thing is that there are two parts in my talk. One was this primordial background, which we are not pushing as the primary target for decihertz. Then nobody is going to give us money. The target is the follow-up, localization, etc. But far into the future, we may be able to see the stochastic background also, which is personally, I am very much excited about it. Now, when all the third generation detectors come online, you see that the target is that they will be able to see all the binaries in the universe. Okay? Now, suppose that is the hope. See, they go.
Sure. Go ahead.
Up to there. Now, the thing is that if that is the case, and suppose you are observing for several years, let's say at some point you have got all the binaries, then in the last few years what was the total contribution from all these binaries in the lower frequency bands. So you would be able to subtract it out.
No, you got it wrong, because that's in the high frequency still. So the decihertz, when you are around kind of 0.1 or something like that,
right.
Those guys, especially neutron star binaries, will not spiral into, in at least in your lifetime, to LIGO when you have to
that is right. That is right. So there the thing was this one, right? This one. See here, let's assume that we have a very precise measurement here. Okay, then you can actually trace back and the exact contribution. This is what is done in CMB. This is precisely what is done, right? I mean, CMB, why we have multiple bands, in spite of the fact that around 100 hertz or 143 hertz, CMB dominates, the other frequencies are simply to get this background so that you can do this extrapolation and subtract it off. So this has to be done in the same way.
Okay, so you're saying that you actually need ET for the decihertz to work.
To do the cosmological background, we need everything in the world.
I see, okay.
We need everything, like whatever, like pulsar. I mean, when I think that will be like one of the ultimate goal of humanity. Every astrophysical information, everything together, when we put in, then we know what happened in the first second.
Okay, so I just go back to, you actually showed that paper, plot from Alberto's multi-band business. Again, that's extremely optimistic, and Anton Klein and others actually looked at it. So this is like what Daniel did for 17017, and so Anton and others have looked at it much more carefully, and this is going to be fairly, definitely possible, but not to the level Alberto was talking about. I just wanted to add to that, yeah.
Right, but here we are not saying that all of these binaries have to be observed and predicted for follow-up. Here only some of them will be fine. See, the thing is that if you don't consider the cosmological background part, there is no problem. It does not have to be all exhaustive, right? I mean, some of them is good enough. I mean, if you miss a large number of binary neutron star merger also, you could still do Hubble constant measurement with whatever you get, even with black hole, by the way. Oh, I actually did not mention this part, that with this Tiango, with this like million kilometer arm length and so on, you may be able to localize even black holes to black hole binary merger to a single galaxy or few galaxies. And that, because the sky localization is so accurate that it is like this is up to 10 gigaparsec, forget gigaparsec, let's say this is around redshift of 1, here you get like 10 to the minus 2 kind of accuracy. Okay, so it is already very good, and also if you have very good calibration, we would be able to get within few galaxies. So then even the black holes can give us pretty good estimate of the Hubble constant.
But that requires completeness of the sample at that kind of redshift. That's also going to be very difficult, isn't it?
Correct. No. You know a merger is going to happen there, okay, in a given position. You put all your telescope there, then the region is automatically sampled. If you put all your telescope time to sample a small cosmic volume, you can get all the galaxies there. You can do 3D survey in that region.
Up to redshift of 7 and things like gigaparsec up to 7?
Redshift of 1. This is
Redshift
like
of 1.
5,
Okay,
yeah.
okay. Yeah, sure, that's fine. Yeah, sure, okay.
So,
Thanks.
Yeah.
Question?
Oh, you have.
You go first since you got it. And then...
So go back to the spectrum. So again, which had everything. You said we need everything in a whatever. But one thing which is missing, you didn't mention in your talk. Okay, so why isn't anyone constructing gravitational wave detectors at microwave frequencies? I mean, they would be much cheaper. You can build them in a laboratory, and again there are models. And I think Emil Motola once asked me 15 years ago about gravitational wave detectors at microwave frequency. I think there was an experiment at Birmingham, but beyond which I think is shut down. But beyond that, I don't hear much.
Possible, but you see, the microwave region.
So even beyond that, it's beyond 10 to the 5. I'm talking about gigahertz. It's not even, the access goes to 10.
Right. So you are saying at the high frequency one.
Exactly.
Yeah, sorry, it's not microhertz.
No, gigahertz I said.
Gigahertz. So the thing is that there are attempts to make detectors at higher frequencies, right? I mean, I think people use the squids and all the kinds of things. I don't know the exact technology they did. But the thing is that there is no guaranteed sources there. You cannot build an expensive detector without a guaranteed source. Nobody.
Yeah, but it'll be tabletop, right? I mean, It won't be a huge scale. It won't be.
Tabletop one, I have only heard informally from people that those have been proposed, but nobody was convincingly could show that technology. And the thing is that if you ask for money, even if it is much smaller than LIGO, still a large amount of money just without saying that that stochastic background will be detected or not, I think there is a much lesser chance of getting any money. There is some high frequency mileage you can get. So there is a proposal, let's say, which is called NEMO, okay, which is at high frequency. But there is a kilohertz, few kilohertz. I think 4 kilohertz maybe. But there is a guaranteed signal there. The neutron stars may, like after merger, there could be a hyper. What is that called? Hyper something that another metastable structure form, and there you get radiation. So you get some signal after the merger. So post merger signal is there. Oh, by the way, for the neutron star part, I also forgot to mention one more thing, that this early observation may also give you a good handle about the precursor emissions from the neutron stars, which are not much discussed, that when in a binary neutron star merger there could be emissions before the merger, also electromagnetic emission before the merger from the crust and so on, which I don't know the full details about it, but those can also give us some handle about the structure of the neutron star and the equation of state, but those are also there. Yeah.
Can I go a quick question? Is there any effort between that range between LISA and PPTA? So there is also a frequency gap, right?
That is right. As far as I know, that there is nothing there. Meaning,
yes.
I don't think there is anything there. But maybe you.
Well, I was just going to say with something like the SKA and daily cadence pulsar observing, we could start to fill that gap, like really high cadence pulsar observing, and something like the square kilometer array, that arm over here, we could start to get into that gap. Yeah.
Yeah. Because that
like right now, this is assuming not much sensitivity and sort of like monthly cadence observing, so we're not really getting down to or up to those high frequencies.
Yeah. In fact, that will be also important because you may need this heavy black hole binary. This shape is also uncertain, so we need to get that also. So if you have two measurements here, then that you can get that also.
Just to add what Shantanu said about the gigahertz detectors, because a lot of the bar detectors and so on have a lot of seismic noise and issues like that, you could just throw it up in space if it's a tabletop experiment.
Correct. That is at kilohertz. Bar detectors are at kilohertz, not at gigahertz. But we were also thinking about doing this project that, since bar detectors are cheap, how many bar detectors you can put and detect some, let's say, stochastic background and so on. But I mean, these are, there is no source like strong astrophysical source at kilohertz. So it will be difficult to motivate such things.
Right.
But then on the other hand, you are right that like student satellite and so on, people can just put bar detectors. But the problem is that each of these detectors, even though they look much simpler than the LIGO detectors, they are still very complicated. You need a cryogenically cooled detector in space, and the detector has to be very heavy. Because otherwise, if the detector is not very massive, the local noise, the Brownian motion is going to affect the detector, right? I mean, anything that is there. So these things we have to, now sending something heavy to space is also not easy. It becomes expensive.
Noise will be understood.
No, meaning like your noise level will be pretty high. Not maybe the Brownian noise or some kind of thermal noise will come. So I forgot, which noise exactly will matter. But the thing has to be heavy because otherwise, any passive noise which is falling on the detector is going to affect the detector. In space, for example, the acceleration on this thing.
So one final question. So why don't we have variable arms in all these space-based detectors? Like you could variation only in one direction. So you have say at 10 kilometers, and then you increase it at 100 once you are done observing at say 10.
No, but the space-based detectors have to observe for a few years to get to the sensitivity which is kind of projected. You cannot observe for some time because these are very low frequency. You need to observe for some certain time. Maybe after 1 year you can change it, but at least for 1 year you have to hold it at the same sensitivity. That is my understanding. Maybe there will be some clever technology which will allow you to go back and forth and things like that. Meaning you observe at some frequency for some time, then you come back, sample it, again go back, but I don't know whether, meaning you are sampling basically at two different, I don't know it is possible or not.
I think it's a technological problem more than a science problem.
And also like you have to have enough fuel in the, meaning the thrusters and so on will be stressed.
Hi. I didn't read much about this H0 estimation from GW observations. How this is done? For example, I read the first paper, first detection. They use the H0 from Planck or WMAP. Probably they had to use WMAP and get to the. I mean, what is the luminosity distance of that source? But you need electromagnetic counterpart as well, right? For that?
Luminosity distance comes directly from the observation, but to detect to look at the host galaxy, you need an approximate H0. Otherwise, you would not know where to look.
But how do you get the distance later? There is no Cepheids or something like that, right? So.
No, so first you get, so suppose you have measured detected a binary signal, right? From the phase information, you have the mass estimation.
Yes,
you know the masses.
Yeah.
From the masses, you know the amplitude of the signal, okay, given the distance, but you have detected an amplitude already in your detector. So from there, you can estimate that what is the luminosity distance to the source. You know the masses, and you know the detected signal, and you know that it ultimately it goes as 1 by r because it is amplitude. So then from there you get directly the luminosity distance.
In that calculation, H0 does not come at all.
That calculation H0 does not come. Then you need but now you want to look at the host galaxy.
Okay.
Okay. Now how will you get to the host galaxy? So there you would need I guess there you will need H0, right? Because otherwise you cannot get there. But once you go to the host galaxy, then you have an independent measurement of Hubble constant, meaning redshift. Once you look at the host galaxy, you measure the redshift.
So by luminosity distance, you look at, take your Hubble Space Telescope and turn it towards that and to find the optical image or
right,
any
so that all these optical, meaning electromagnetic telescopes can then give you some lines, let's say you know some lines, and then from those lines you can get the redshift. And then from that redshift you get, then you take the ratio and get the Hubble constant. But you are not using any Hubble constant measurement from Planck or this is independent measurement.
No, but in the where there is no electromagnetic counterpart, the first paper that used H0, that used H0 specifically from Planck in order to estimate the distance or the redshift of that incident. I mean the first event in 2015. Because that time this Virgo was shut down, only Livingston and the Hanford was operating. So they said we could not get the exact angle, so there is a inclination was not well understood.
No. Virgo was active at that time. Without Virgo, you would not get the sky localization.
No, the first one.
Oh, the first one. Right. First one, Virgo was
that used H0 in order to understand the place where it happened.
Okay. Yes, there you have to, because there is no electromagnetic counterpart there. But I am saying when there is for the binary, where meaning binary neutron star merger,
yes,
there it was not. It is a different thing. But the first one, you only got the luminosity distance. In order to say at which redshift it is, then you need H0. So that's all.
And the electromagnetic counterpart, if you have, then you can understand the galaxy where it is, the host galaxy as well. That is what you are saying.
If you get the host galaxy, then from electromagnetic observations, you can get the Hubble constant.
Okay, is it better than the Cepheid calibration? Are there more,
it's an independent measurement. I mean, right now, high redshift and low redshifts are giving you completely different answers. High redshift measurement is giving you whatever 68. The low redshift is giving you 73 and things like that.
Yeah, that I understand. I'm just saying that this host galaxy identification, how reliable that is. So that is one, because for very that is something that I was.
So that is there, but it was kind of because you see from different.
you have a spectroscopic redshift also.
Okay. Yeah. So thanks. I mean, I just wanted to know. I have to read this in much greater detail. Otherwise, yeah.
So this was like just to. I mean, I thought Varuna must have covered this, so I did not get into this. But this is how this was Fermi. I mean, initially it was actually LIGO detected first, but it takes time for LIGO to give you the error circle. So then with LIGO, what I said before is that Virgo did not observe this, but since it was sensitive, it was enough to cut out this part, and that's how you got the source. And then there were these galaxies which were followed up, and they found where they saw a movement. Meaning, if you observe in that region, then they saw that there was a movement, meaning change in luminosity or whatever in one of these galaxies. So that gave you the host galaxy.
Okay. That's neat. Thanks.
Yeah.
Sir, what kind of science you are actually expecting, like progenitor of type 1a supernova, something you have mentioned in a...
That's also there, right?
Okay.
What kind of?
What kind of science you are expecting? I mean, through the progenitor type 1a supernova, by means of...
So the binary, so type 1a has is in binary, right?
Mm-hmm.
So that binary is, you will be able to detect in this, in the decihertz band.
Okay.
So white dwarf are possible to detect.
Okay.
Oops, sorry.
Okay. So any science related to white dwarf?
Science, made lot of science related to white dwarfs are possible in that. But I forgot like all the things that can be done. But essentially for type 1a, so type 1a is also crucial for cosmology.
Mm-hmm.
I don't know whether we will get some input for the type 1a also. But type 1a supernovas you could. Meaning before the supernova, you could get the in spiral part here.
Okay. That's.
Are there any Zoom questions?
Oh.
No one's on Zoom? Okay. I think that's it. Let's thank our speaker again.